All right, today we're going to discuss topics that very often confound the student in Organic Chemistry 1, the relationship between alcohols and alkyl halides. Alcohols abbreviated ROH, as opposed to alkyl halides abbreviated RX, where the OH obviously refers to the hydroxyl, the X refers to the halide. Now, the one thing they both have in common is that the functional group, the hydroxyl and the halide, are both considered to be nucleophiles, which means that in a bond between the oxygen and the carbon, or the oxygen and the halide, you're dealing with two very electronegative species, the oxygen and the halide, thus forming what we like to think of as a dipole, creating a partial negative charge within the halide and a partial negative charge within the oxygen, and the carbon in both cases have a partial positive charge. Now, the two can be interconverted, meaning it's totally possible to take an alcohol and in the presence of a hydrogen halide, such as hydrochloric acid, hydrobromic acid, we'll get what we call nucleophilic substitution, which is just a nice way of saying we're switching out the hydroxyl for the halide. And again, this is classified as nucleophilic substitution. Now, as you can imagine, it probably isn't quite that simple. Let's look at the mechanism involved with nucleophilic substitution for a moment. The hydrogen halide is also doing more than just providing the halogen within the alkyl halide. It's also acting as a type of catalyst. Now, oxygen, or I should say the oxygen found in the hydroxyl, is extremely electronegative, which means it's going to have a tendency to hold on to the carbon of the alkyl group very, very tightly. In other words, it's going to be a very poor leaving group. What we have to do is figure out how to make that hydroxyl ready to let go of its carbon. That's where the hydrogen halide comes into play. Since the hydrogen is going to be somewhat positively charged or electrophilic, and the oxygen within the hydroxyl group is going to be nucleophilic, we say that you get nucleophilic attack. In other words, the oxygen from the hydroxyl is going to extract a proton from the hydrogen halide, thereby breaking polar covalent bond. And for a brief moment in time, you're going to have what we call a protonated alcohol. And of course, as a byproduct, you're going to have your anionic halide. Now, you may be thinking that the protonated alcohol looks a little bit like water. And if you are thinking that, that's a very astute observation, because while hydroxyl groups don't make the best leaving groups, water does make a fairly decent leaving group. And nearly spontaneously, the water will leave its alkyl group and the alkyl group will have a carbocation. Now, as you can imagine, carbon doesn't really like being a cation very much. So it's going to be looking for something to provide it with whatever electrons were taken away by the water. And perfect candidate is this halide anion that came from the alkyl halide, I'm sorry, the hydrogen halide. And as the saying goes, opposites attract. And in the end result, you get your alkyl halide. Now, word of warning. Does this mechanism hold true for every type of alcohol and every type of hydrogen halide? Not necessarily. If you recall in a previous discussion regarding carbocation ion stability, the type of or classification of the carbon does matter significantly on its stability as a cation. In other words, tertiary carbocations are going to be more stable than secondary. We get rid of some of this. Secondary carbocations are going to be more stable than primary, and the primary are going to be way more stable than methyls. Now, how this plays out or how this transfers over is we have to look at the classification of alcohol. So if we want to convert an alcohol into an alkyl halide, we need to first assess whether that alcohol is going to be tertiary, secondary, primary, or methyl. Now, let's say, for example, we are looking at a tertiary alcohol. For example, let's say we take something simple, like T-butanol. Nobody will argue this is a tertiary alcohol. If T-butanol is allowed to react with, say, hydrobromic acid, that's your hydrogen halide, the mechanism will follow the mechanism that we just outlined, in which the hydroxyl oxygen will remove the proton from HBr, leaving behind your anionic halide and a protonated alcohol. Now, because we're dealing with a tertiary alcohol, and tertiary carbocations tend to be fairly stable by comparison, then spontaneously we can expect water, that water molecule, to leaving us with a tertiary carbocation, which which again is the most stable of the carbocations, leaving the cation to be attacked by our bromide, hence forming T-butyl bromide. Now, in the case again of using a tertiary alcohol to make a tertiary alkyl halide, this is still considered to be nucleophilic substitution, but specifically this is what's called an SN1, or nucleophilic substitution first order. SN1 is pretty much resigned to dealing with tertiary carbocations, tertiary alcohols. What if you're not dealing with a tertiary alcohol? So similar reaction, only difference is let's replace one of the methyl groups with a hydrogen. So now I'm dealing with isopropanol, which is a secondary alcohol. Will the reaction be the same, or will the mechanism be the same? Yes and no. Yes and no. Here's the problem. I'll still get my protonated alcohol. Here we go. So I'll still get protonated alcohol, which is protonated isopropanol. Now, with the tertiary, the water leaving group left spontaneously. Will that be the case with the secondary alcohol? Well, in terms of stability, we said the most stable carbocation was the tertiary. Secondary carbocations are not nearly as stable, so we may not want to run the risk of forming a secondary carbocation. Instead, what we may want is to allow our bromide to come in and attack the carbon bearing the water molecule nucleophilically. So we get nucleophilic attack on this carbon. So the bromide comes in, spontaneously pushes out the water. So we really never get a carbocation forming, which is good because we don't want an unstable carbocation. And we still get the alkyl halide of choice. Now, this type of nucleophilic substitution in which a carbocation is not formed is referred to as SN2, or nucleophilic substitution second order. For the most part, we can say SN1 will favor tertiary alcohols. SN2 basically is everything else. So secondary, primary, definitely methyls will follow an SN2 type mechanism if the desire is to convert an alcohol into an alkyl halide. I hope this discussion was informative. Please try to do as many examples on your own as you can. And if you still run into problems or issues, hit me up. I'd be happy to straighten them out for you. Until next time.